All right, so this is the topic 1 video for lesson 4. And in this lesson, we're going to talk about, in this topic video for the lesson, we're going to discuss physics through the lens of calculus. And I don't think it would be possible to overstate the very close and important relationship between calculus and physics. In fact, when I was in high school, I took the physics AP exam, and there are two choices. You can take what they call just a regular physics AP exam, or you can take the calculus-based physics AP. And I was told not to worry about the calculus-based. I was already taking calculus, and so I did. I went ahead and took the physics AP. I passed it. I went to college, and I was enrolled as a math and education double major. So I was there as a mathematics major, and they told me, sorry, we can't accept your AP grade because you are a mathematician. You need to take physics through the lens of calculus. And they made me retake the entire course called Calculus-Based Physics 1. Essentially, that was like, I don't know if that was the official title or that was basically what it was. And I learned all the same material, but I will say it was a different class because instead of just, where in a non-calculus based physics class, we might just be asked to memorize a whole bunch of different formulas. In a calculus-based physics class, we start to realize that there really is only one formula for a category, and maybe the 3 or 4 other formulas that we had to memorize, they were actually just derivatives of the first equation. So we memorized 4 and we really only needed to memorize 1 because all the other ones were so closely related. So I share that to say I'm really not overstating that relationship between physics and calculus. It is there right in the very foundation of everything that we do in physics. There's a mathematical component to it, and that's why there are so many formulas. So, that being said, I want you to take a look at this screen here, and I'm going to draw a picture. Oh, let's clear the lower third again. Let's think about, this is a classic physics problem. So if you have taken physics, you probably have seen something like this. We have a giant hill, and we have a person up here on the top of the hill. And they are trying very hard to reach out over the cliff. Don't you like their awesome expandable arm? I mean, I wish I had arms like that. I could really do magical things in taking care of my crazy kids. Okay, so this person is hyperextending their arm out over the cliff and is about ready to drop this object. And once they do, it is going to fall down. Not at a diagonal line, but for some reason my line just drew at a diagonal line. So we're just going to pretend it's falling diagonal like that. So he goes to the edge of the cliff, drops the object, and it falls. And we know, if we've spent any time working through physics problems, that it doesn't fall at a steady rate. In fact, it starts off, maybe in the first second it goes this far, and in the second it gets this far, and by the third second it's already thud hit the ground. So things tend to accelerate as they're falling with gravity. Okay, so thinking about that picture in our mind, let's talk about some of the mathematical phrases we would use to describe what's happening. And I actually just gave one away, so hint, hint, I may have already got you going with some important physics words. Okay, that's a slightly straighter line this time. I'm creating my little derivative ladder here, and we're going to compare it to what we see in the picture. So in physics, one of the most foundational concepts we have in this type of physics, like the whole physics of dropping an object, say, or throwing it into the air, projectile motion in a sense, the most foundational piece of information is the position of the object. And that's kind of what I drew with the red arrow there. We have an object that's falling, and the easiest thing for me to observe is the exact position of the object. Like I could freeze frame it and see where that object was going. It's very easy to identify that. And we call that in physics position. That's the official term. And we usually label it with the letter S, which I know is weird. Why not P? It's because we have other things that we call by the letter P that are really important. Position we might also talk about as like displacement from an original position. So we have that letter S in position and displacement. So if that helps you remember the S. So position we refer to as the S of the object. That means exactly where is the object at 1 second, at 2 seconds, at 1.123 seconds. Where can we figure out where that object is? That's the most basic part of physics. But we also care about things like how fast that object is going as it's changing position. Now, as soon as we start to talk about changing something, we're discussing a rate of change. And since we care not about just average change between when it was at the top of the hill to when it was at the bottom, we care about instantaneous accuracy, about the velocity of this object, how fast it's going, the velocity. We are talking about a derivative. So the next important thing that we need to talk about in physics is velocity, which we do represent with the letter V. So we'll say V equals velocity. But what is velocity besides just saying, oh, it's how fast we're going? Well, velocity is the rate of change of position. In fact, it is the function that, if I had a function that described position, the function that describes velocity would be its derivative. So V is essentially S prime. It's the derivative of S. Velocity is the derivative of position. And that's true all the time, not just in this particular situation. And we could actually, we probably will do this in class just for fun because it's kind of exciting, especially if any of you are already taking physics. You can take the equations that we have for position and just derive them with respect to time, and you'll get the velocity equation. So if you've ever had to go through the process of memorizing those equations, you'll know what I'm talking about if you've done it already. You didn't actually have to memorize it. You could just derive it and get the answer. Okay. Hope I haven't disappointed anybody by saying that. So if we have position, that's the most basic part of this aspect of physics, this kind of projectile motion, dropping an object kind of physics. Position is where we start, but if we want to know the rate of change of position, we get velocity. You change position, you get velocity. Now what happens, think in your mind, is velocity always constant or does it change? Well, in our case, which we showed over here on the little person stretching way out over the cliff to drop an object, the velocity is changing. The speed as it goes, we can see it because the position is not changing at a steady rate. In the first second, it makes a little bit of progress, but in the second second, that's difficult to say actually, it goes much further. It makes a lot of progress because the speed or the velocity is increasing. So velocity is not constant, or it doesn't have to be. Velocity changes. And what do we get when we get a change in velocity? Well, for one, we're taking a derivative, right? Right now we're talking about taking V and finding the derivative, which just so happens to also be the second derivative of position if we want to be nice and thorough with our chart. We have position, we take the derivative, we get velocity. We find the change in velocity, we get some beautiful thing we call acceleration, which in this case happens to be acceleration due to gravity, but acceleration of a car can be positive or negative. Remember, velocity can be positive or negative too. I should have thrown that in, right? Positive velocity takes you forward in whatever, or up in whatever direction you're considering the positive direction. Negative velocity takes you the opposite of that. Acceleration is the same way. We can increase our velocity, we can decrease our velocity. If we're increasing velocity, we have a positive acceleration. If we're decreasing velocity, we have a negative acceleration. So what are we talking about here? We're talking about the derivative of velocity. We're taking the rate of change of velocity. Now, acceleration, another easy one to remember, we label it as A for acceleration. And those are really the three most important parts of this foundational thing that we always seem to talk about this first in physics: position, velocity, acceleration. And right there you see everything about it is related to rates of change, which means that it's based in our knowledge of derivatives. So if I had the equation, which I don't have right now because I'm trying to talk about this more theoretically at this point, we'll be a little bit more specific in topic 2 video. If I have a position equation and I derive it, I automatically have the equation that describes velocity. And then if I derive it again, so I take the second derivative, I've now moved from velocity to acceleration. So I can have my equation for position, my equation for velocity, my equation for acceleration. Normally in physics, we don't actually go any further than that, but we do know it is possible to continue to take derivatives. And there actually is one more derivative here, so not the first or the second derivative of position, but the third derivative of position, which would also be the second derivative of velocity and the first derivative of acceleration, again, just for the sake of being complete. You're probably wondering, what would that be? What happens when we change acceleration? And in fact, I almost want to tell you to pause the video for a moment and try to think, when have I experienced a change, not in velocity? So if we change speed, we get acceleration. But have you ever experienced a change in acceleration? You probably have. And in fact, if you're picturing it right now, this word that I'm going to give you is going to bring a very vivid picture to your mind of what the change in acceleration felt like. The derivative of acceleration is something we call jerk. Not like a really annoying person, although I have been known to possibly be the instigator in having my calculus students insult their friends by calling them the derivative of acceleration. So if you're really mad at your friend, they're not taking calculus, and you don't want to go so far as to call them a jerk, you could potentially call them the derivative of acceleration and really accomplish the same thing, which I'm not condoning as necessarily a very nice thing to say to your friend, but it is something you can tuck away for future reference. Okay, the derivative of position is velocity, because you change position and you get a type of speed. Velocity, because it can be positive or negative. You change velocity, you take the derivative of velocity, and you get acceleration. But if you change acceleration, let's say you are moving in the positive direction and you're accelerating your car, and you're not racing, because you shouldn't be racing your car, but somebody is racing their car, accelerating it, getting faster and faster, and then all of a sudden a squirrel runs across the road, and this racer is a kind, compassionate soul, and they decide to suddenly decelerate their car. So they went from accelerating, their velocity was increasing in the positive direction, to slamming their foot on the brake and creating some negative acceleration to bring their velocity back down to zero. You experience this very fancy physics experience, I can't think of another good word, called jerk, because you jerk in the car when you slam your foot on the brake. And that is when you have experienced the derivative of acceleration, besides if your friend just did something annoying. But okay, that is my outline. That little ladder right there, that's all you really need in your notes. It should say position, velocity, acceleration, jerk. If you have that outline and you understand the way those are connected, then you are good to go. One thing I want to kind of put as like if you have a little asterisk, you can put, put a little asterisk here on velocity and make this subnote. In some of the problems, the example problems we're going to talk about, they will refer to velocity and they will refer to speed as two separate things. And that's good. Velocity and speed are not exactly the same. In fact, if I want to define it mathematically, what I would say is speed is equal to the absolute value of velocity. Absolute value, we know, means that we're always going to get a positive answer. So even if the velocity is negative, meaning we're traveling backwards, let's say -4 meters per second, speed would say we're going 4 meters per second. So what speed does is it takes out the aspect of direction and just looks at how fast we're traveling. Not directionally, but just how fast. What's the absolute value? So I want you to have that little addendum at the bottom of your notes so that as you look at example problems, which we will look at one in the topic 2 video, that doesn't throw you off when you see velocity and speed being talked about as two different items. Okay, that's it. You are done with the topic 1 video, and now you can look at the examples in topics 2 and